In 1923, Frank Whittle joined the Royal Air Force. The 20s and early 30s were the formative years of the RAF. It was small, select, highly trained. RAF aircraft followed the fashions of the day. No longer constructed of wood, it is true, but still fabric-covered, wire-braced biplanes, differing little in essentials from the machines that had fought over the trenches in the closing stages of the Great War. On joining the RAF as an aircraft apprentice, Frank Whittle was trained as an airframe rigger, a trade he was never in fact to practice, for on completion of the 3 years course, he was selected to a much-coveted cadetship at the then newly created RAF College at Cranwell, where he learned to fly and was duly commissioned as a pilot.
So I first went solo on the Avro 504K, and then on the Avro Lynx, then from there to the Bristol Fighter, then the DH-9A, and then on to the Siskin in my last term.
To be an RAF pilot was in those days a most agreeable position for a young man, flying from neat grass airfields all graced with well-appointed messes, a chain of exclusive flying clubs stretching from Britain across the empire. The biplanes of the 30s, like these Hawker Harts, could achieve sea-level speeds of around 180 miles an hour. The fastest single-seater of the time only managed just over 200. But as they climbed into the thinner air, their performance dropped drastically, a characteristic of the piston-engine propeller combination. Frank Whittle, while a cadet at Cranwell, had written a paper, Future Trends of Aircraft Design, in which he had predicted speeds of up to 500 miles an hour. This would be impossible to achieve with biplanes due to the drag inherent in their design. For however powerful their engines, the maximum speed of a practical biplane would be limited to around 250 miles per hour. The 1929 Supermarine S6 Schneider Trophy seaplanes were to prove the point. That year, their 2,300 horsepower Rolls-Royce R engines had enabled them to win the trophy at 340 miles an hour. Later, in 1931, with still more power, one of them became the world's first aircraft to exceed 400 miles an hour in level flight. Yet in a sense, the Supermarine S6s were a red herring. Their very success obscured the fact that their performance was very nearly the practical limit obtainable, a fact that Cadet Whittle had realized at Cranwell.
One of the things that I did was work out what I now know as the well-known Breguet equation, which indicated that if you wanted to fly both fast and far, you'd had to fly at such a height that it was quite beyond the and at such a speed that it was quite beyond the piston engine and propeller combination.
In Germany, Fritz von Opel had in 1929 constructed an experimental aircraft to demonstrate that powered flight without a propeller was a feasible proposition. Opel used a number of solid fuel rockets to power a glider. It flew just, but its maximum duration of 10 minutes hardly foreshadowed an aerodynamic revolution. Opel's experiments made no impression on the aero engine manufacturers, who continued to construct their heavy, intricate piston engines, though now employing the new technique of supercharging, that is, using impellers, high-grade paddle wheels driven by the engine, to pump the petrol-air mixture into the cylinders in an attempt to maintain sea-level performance in the thin air of high altitude. However efficient the designers and metallurgists made the power plants, the weak link at high altitude, the propeller, remained. Searching for an alternative, Frank Whittle at first considered using a piston engine to drive a compressor, pumping air into a jet pipe with burners, but he rejected the idea as hopelessly inefficient, which indeed it was. That proposition had been one considered in his Cranwell paper.
I didn't have the complete idea then. I was just groping towards it. Then in 1929, the penny dropped, and the idea of the turbojet came to me.
But the principle of jet propulsion had been discovered much earlier in 120 BC by Hero of Alexandria. His engine consisted of two small jets angled from a globe of silver, fed by a boiler through supporting pillars. With pressure up, the steam jets propel the globe. Thus man's first known heat engine was jet-propelled. 1600 years later, Sir Isaac Newton formalized the effect as his third law of motion. For each action, there exists an equal and opposite reaction. And if James Watt's celebrated observation of the boiling kettle's lid had applied Newton's law instead to the spout, he could have invented the turbine. Like this simple steam turbine, the gas turbine which Frank Whittle proposed is extremely simple, having only two major moving parts. The compressor wheel on the left and the turbine on the right, both keyed to a single shaft and housed within a pressure casing. The compressor's impeller forces air into the casing, which also contains a number of combustion chambers in which fuel, kerosene, is continually burnt. The expanding gases resulting from combustion pass through the turbine, turning it at very high speeds, up to 17,000 RPM, before exhausting from the jet pipe with enough velocity, 1,000 pounds in the early engine, to push the aircraft forward in powered flight. In 1930, that was still all theory. Undaunted, Frank Whittle patented his gas turbine on the 14th of October in that year. The high-speed monoplanes, which could conceivably utilize a jet engine, now existed, at least in prototype. But Frank Whittle knew that to construct a practical gas turbine aero engine was going in many ways to be a much more formidable undertaking. The massive 36-litre Rolls-Royce engine, which had powered the Schneider Trophy seaplanes, had required the most intensive research, not only into the very special chemistry of the fuels, but also into the then unknown territory of high-pressure supercharging. Rolls-Royce, with the aid of the Royal Aircraft Establishment, finally, after a great deal of work, managed to achieve a supercharger that could efficiently compress the mixture to twice sea-level atmosphere, and that in 1929 was considered to be very good going indeed. Frank Whittle had calculated that for his gas turbine he would require a much larger and far more efficient compressor, working at 4 times that pressure. The calculations for the compressor were included in a paper which Whittle wrote to prove the case for the gas turbine. But none of the aero engine manufacturers were in the least interested in his proposals at a time when meagre orders for existing engines were hardly sufficient to keep the firm solvent. One obvious conclusion drawn from the Schneider Trophy was that the days of the biplane were numbered. The Air Ministry was therefore experimenting with monoplanes like this long-range Fairy. To spend the money instead on exotic engines, which could at best take years to develop, was out of the question. So to cool his ardor, the Air Ministry posted their young inventor to the Marine Aircraft Experimental Establishment at Felixstowe to discover how a land plane behaved in water. Frank Whittle also made 47 experimental catapult launches. One was to prove memorable, for his passenger was thrown out but managed to grab hold of the tailplane as he left.
I took a quick glance over my shoulder and I saw there was a body on the tailplane, but I didn't know it was my passenger. Until I found I wasn't losing control entirely. I got the stick right forward, full throttle. I took a more collected look and saw that it was my passenger, who then was struggled round into a sitting position with his back against the fin wire. And when he saw me look round with his helmet blowing out and his cheeks blowing out, he gave me a thumbs up sign with his spare hand. The other one was holding onto the fin. And I saw him go, okay. I thought to myself, well, you may think you're okay, old boy, but we can't get down. Because every time I tried to pull the throttle back, I couldn't hold up his weight.
He couldn't turn either due to his passenger leaning on the rudder, which was embarrassing since a German liner was dead ahead. The question was,
could I get back onto the water before I flew into the side of the ship? I managed it. The German ship turned to port, which was taking a bit of a risk in those shallow waters. This was just off the Isle of Wight.
In the summer of 1932, Whittle was posted to an engineering course at Henlow, which he passed with 98% marks. He then went up to Peterhouse College, Cambridge, to read for a mechanical engineering tripos. During those 4 years of study in that biplane era, Frank Whittle deplored the lost opportunities and had, by 1936, begun to face up to the reality of the continued rejection of his gas turbine engine.
I began to think it was before its time. In fact, I allowed the patent to lapse. And then along came Dudley Williams, now Sir Ralph Dudley Williams, or at least he wrote to me first. And then I saw him afterwards. He said he thought he could raise some money to get the thing going. And he and a partner did, in fact, manage to contact a small outfit called, commercial bankers called Falcon Partners. And they agreed to put up some money. And as a result of that, Power Jets was formed in March of 1936. But before the company was actually formed, Falcon Partners agreed to place an order with the BTH for the manufacturing drawings of an experimental engine.
To this day, Sir Frank still has the original drawing board, which was in 1936 Power Jet's principal asset.
The first jet engine was drawn on that. The BTH first drawing I wasn't satisfied with, so I did a half-scale drawing on this board, and that was the basis of the experimental engine. Power Jets had no staff except me, and I was on loan from the Air Ministry as a squadron leader.
So the initial practical work was contracted out to the British Thomson Houston Company at their Rugby's steam turbine works, where gradually the strange engine took shape. Casing, combustion chamber, the impeller of the compressor, and the turbine. By the 12th of April 1937, the engine stood complete and ready for testing. The question nobody liked to ask was, would it work?
When we first tried to start it up, we certainly succeeded. I was on the controls, and we got the thing running up to 1,000 RPM, and I got a signal from one of the fitters that there was a light up in the combustion chambers, and I signaled for the speed to be raised to 2,000 RPM, which was done with an electric motor. And then I opened the main fuel control to get it going under its own power, and it certainly did. It accelerated out of control, and so did everyone standing around. Except me, I was paralyzed with fright. I thought maybe we'd got something which we couldn't control. It went up to about half full speed after about 8,000 RPM, and then fortunately stopped accelerating. The reason was that there was a lake of fuel had collected in the combustion chamber which we didn't know anything about.
On its second run, the engine seized solid at 12,000 RPM. It was rebuilt and then run up to 13,000 RPM with, Sir Frank remembers, a noise like an air raid siren. After those early test runs, the BTH management, not unreasonably, decided that a move to a rather more rural location was perhaps desirable. In the village of Lutterworth, the company owned a derelict property known as Ladywood Works, the name being a great deal grander than the location.
Oh, God, it was terrible. It was an old, disused iron foundry. They were the rickety old floors. Old Whittle had an office rather like a rabbit hutch, you know, and it was a really terrible place. It had one test bed, as I remember. I can't remember what the workshops were like, but it was a pathetic setup, really.
With delays caused by the move and the chronic shortage of everything, especially money, it took a year to rebuild the engine, which seized up, to be yet again rebuilt in its third and final form, to become the prototype of the engine which would eventually fly, with the 10 interconnected combustion chambers. These were to prove one of the most difficult components of the engine to get right. This is that original Whittle engine, the first in the world to run, now preserved in the Science Museum, London. Incredibly, in spite of being constructed from salvaged parts, it ran remarkably well.
It was getting up to speeds of about 16,500. By the time we were getting it to this stage, it had been through so many mishaps that it was really a heap of junk. And so when I look back on it, it rather surprises me that we got it up to 16,500.
That was in June 1939. By then the Germans had annexed Austria and the Sudetenland of Czechoslovakia. The Munich crisis of September 1938 had passed, and of the peace in our time, then predicted by Neville Chamberlain, just 3 months remained. Since 1933, when Hitler first came to power, the Luftwaffe had been training and growing, secretly at first, then openly, until by 1938 it was revealed to have achieved and surpassed parity with the RAF. There was to be little doubt as to the quality of the Luftwaffe. For example, the Stuka dive bomber, which was soon to spearhead the Blitzkrieg, and the Ju-88, conceived in 1935 as a Schnell bomber, a bomber with the performance of contemporary fighters. To counter the Luftwaffe expansion, the RAF began to rearm. In 1936, the prototype of R.J. Mitchell's Spitfire had flown, as had the Hurricane, and both were now in full production to re-equip the fighter squadrons of the RAF, many of which were to fly biplanes until mid-1939. In the 12 months' grace between Munich and the outbreak of war, the long years of neglect of the RAF were to some extent made good. By September 1939, Fighter Command was at last equipped with modern aircraft, backed by an efficient radar-based fighter control system, and was considered to be able to counter the Luftwaffe. However, if anyone at the Air Ministry had thought that the German aero engine industry might have made the transition from their turbo superchargers to a gas turbine and be producing a German jet, then their appreciation went unheeded. In point of fact, the Germans had already made that step. It was the experimental Heinkel 178, powered by a jet engine designed by a young physicist from Göttingen University, Hans Pabst van Oene, who in 1936 had approached Ernst Heinkel with a proposal to build a gas turbine. Heinkel agreed to provide the facilities and finances for van Oene to build an experimental turbine which ran on hydrogen. The turbine produced only 176 pounds of thrust, but it impressed Heinkel sufficiently for him to back the development of a flight engine. With the backing of a large aircraft factory, the engine, similar to Frank Whittle's, was built and bench-tested by the winter of 1938. On completion, the engine was installed in the specially built HE-178, which was ready by the 27th of August 1939 to make the world's first gas turbine-powered flight. Van Oene remembers the day well.
Well, we had a short airfield. Wasitz had already, the day before, taxied the aircraft, and he thought he could make it. It was an early morning, slightly foggy, but only very slightly foggy. And he accelerated. It worked without any, it looked without any problem. He lifted up, and then we lost him because we went on straight and we didn't hear anything anymore. And so we waited, and then 5 minutes, a very long time, then he came back, then he curved around, and we wondered why he is not landing. And so we felt, oh, he feels very good there. But the fact was that he couldn't really see, because the glare of that fog, he said, was terrible. The sun came up, and when he wanted to land, it was such a glare he couldn't really exactly see the airfield. So he made several rounds until he could really safely set down.
Test pilot Wasitz, Heinkel and van Oene celebrated with a champagne breakfast, perhaps a little prematurely, for 5 days later Germany was at war. In stark contrast to the plenty enjoyed by von Ohain, Frank Whittle struggled with his single battered engine and was in those last weeks of peace suffering from an early example of catch-22.
Because the power jets was on the point of going broke, the Air Ministry was very reluctant to place any contracts, you see. They thought the firm was too rocky. But we were getting small contracts, you know, £5,000, and then they paid for the second reconstruction of the engine, about £2,400. And altogether, by the time the engine was showing signs of being worthwhile, we'd spent about £20,000, all told, private money and Air Ministry money. But the real turning point was when the Director of Scientific Research came to Lutterworth, where we were testing the engine, and saw it run up to 16,500 RPM, and he became, for the first time, completely sold. Up to that time, they'd been paying the money on the basis that the job was really long-term research.
One result of that official visit was that all of Power Jet's work became subject to the Official Secrets Act, which made raising capital even more difficult. But the Air Ministry had at least bought the long-suffering original engine and had placed a contract for a flight engine, the W1, to power an experimental aircraft which the Gloucester Company were to design and build, the Gloucester Whittle E-2839. But it was still on the drawing board when the Second World War broke out, and all that Power Jets had was a model. The war, at first, at least in Britain and France, called the Phony War, was soon to change, to become the reality of Dunkirk and the Battle of Britain. That summer, Frank Whittle and his small staff still had the problem of finding an established aero-engine manufacturer, for although the E-2839 had yet to fly, it now had a successor, a twin-engine fighter, eventually to be named Meteor, to follow the purely experimental Gloucester Whittle. The obvious choice, Rolls-Royce, were like the other major companies fully stretched, supplying aero-engines for war production. Another difficulty was Frank Whittle's concern that a big company might absorb Power Jets, whose patent position was far from satisfactory.
The patent position was not strong. The first master patent having lapsed. We had several other patents, but I didn't think that the patent position was very strong. So we were looking for subcontractors who were not likely, as we thought, to start competing with us. And it's happened that the wife of one of our directors was a friend of the wife of a director of the Rover Company, and as a result of that, we invited the Rover Company to act as subcontractors to us, which they agreed to do. The Rover Company, I'm afraid, made a shambles of the job, and their behaviour was, I think, absolutely disgraceful. They were out to get direct contracts, which they succeeded in doing. They did all sorts of dirty tricks. For instance, they got permission from the ministry to be responsible for the drawings. Well, on one occasion, manufacturing drawings, on one occasion we asked them to let us have a drawing of the compressor casing. And when it came, we found that it was, you might say, a breach of copyright, because it was in one of a photostat of one of our own drawings, with all reference to Power Jets removed, as though it were a Rover Company drawing. But unfortunately for them, they'd left in the bottom right-hand corner the names of our draftsmen, so that it was pretty obvious that it was merely a photostat of our drawing. And after that, I became much keener on getting Rolls-Royce into the picture.
The first Rolls-Royce man to visit Power Jets was Stanley Hooker.
Well, it was in January 1940 when Hayne Constant, who was the Director of Engine Research at the Royal Aircraft Establishment, took me to Lutterworth to see the engine. I'd never heard anything about it before. Constant used to come to Derby to discuss the Merlin supercharger with me. And one day he said, I'm going to take you to see this jet engine, which was secret at the time. that I met Whittle, and then he showed me his engine and discussed it with me, described it and so forth. And I can't say I was an immediate convertee to jet propulsion. I hadn't really studied it sufficiently for that. But I must say that standing by his engine when it was running, and they used to run more or less in the open in those days, one always had a sensation here was tremendous power, you know.
Stanley Hooker's brilliant work on the supercharger for the Merlin shared common ground with Whittle's jet compressor.
Lutterworth wasn't very far away, of course, only 30 miles or so. And I, having met Whittle and got on very well with him from the beginning, I used to go and see him fairly frequently. In fact, I used to take him Merlin supercharger the results to look at, because, you see, he had no tests of his own supercharger. There wasn't a plant big enough in the country to test it. So I used to take him these things, and we had a lot of discussion. And eventually, when his engine was running at about 1,000 pounds of thrust, I went to see Hives, Lord Hives, or Mr. Hives as he was at the time, and tried to persuade him to go to Lutterworth and see the engine. And he said, what does it do? And I said, well, it's giving about 1,000 pounds of thrust. Well, now, we were all used to horsepower. We knew the Merlin gave 1,000 horsepower more. And one must admit that 1,000 pounds of thrust doesn't sound much compared with 1,000 horsepower. And Hives turned to me and said, well, that's not much, is it? You know, they wouldn't pull the skin off a rice pudding, would it? And I went away and did a sum, went back to him and said, do you know how much thrust the Merlin gives in a Spitfire? And he said, no, how much? And I said, 1,000 pounds. And he immediately rang for his secretary and said, I'm going down to see this engine with Hooker on Sunday.
And what was Hives' impression?
Oh, he went down, almost he came, he saw he was conquered, you know, it was literally that, really. He didn't say much, he walked around, Whittle described it all to him, gave him proper tour. At the end of it, he turned to Whittle and said, I don't see many engines about, Whittle. He said, why haven't you got more engines? And Whittle said, well, I look at the facilities I've got. I can't get anything made, I can't get this, and I've got no money, and so on and so forth. And Hives turned to him and said, well, send us the drawings and we'll make the stuff for you. And we made quite a lot of components at Derby for Whittle to help him with his job.
The Battle of Britain was by then at its height. The epic victory of the Spitfires and Hurricanes requires no retelling here, but it is pertinent to ask, if Frank Whittle had been better supported, could a developed British jet have made any difference to the struggle? In the absence of German jets, probably not. During the battle, there was never a shortage of RAF aircraft, but of pilots, and the existing Spitfires and Hurricanes carried the day, which was just as well, because the Gloucester Whittle was not rolled out until the spring of 1941, fitted with a non-flight Whittle engine, the W1X, to commence taxiing trials.
It was really a lash-up engine, which is why we call it the W1X, W1 Experimental. And that was used for the taxiing trials of this aeroplane.
It was taxied at Hucklecote on the 7th of April 1941 by Frank Whittle. He opened the W1X engine to 13,000 RPM, but the grass airfield was soggy and the best speed obtained was a mere 20 miles per hour. The next day, Gloucester's test pilot opened up to 15,000 RPM, and it was clear that the flight engine should provide adequate thrust for flight. As it was, it would seem that the W1X also had hidden reserves, as witnessed by Bob Fielden.
When the pilot, Jerry Sayre, did just a short hop on a grass airfield, jet-propelled. That really was one of the moments of my life. And I might record that afterwards, one of the other pilots, Mr. Michael Daunt, said to me, "Thank God it flew straight." I said, "What on earth do you mean?" He said, "Well, we all thought it was going to squib around like a squib firework."
The W1X engine used for the taxiing trials was removed from the aircraft and sent to the United States, and the 1,000-pound thrust W1 flight engine was installed in the prototype. Ground running had proved that the W1 engine would have no difficulties providing the minimum thrust, around 900 pounds, required for flight. This unique colour film of the original E-2839 was taken by a Power Jets engineer, Matthew Nathan, after the first flight made at Cranwell just 40 years ago.
On the day, 15th of May, 41, the weather during the day was too bad for other than taxiing trials until the evening. And then Jerry Sayre just tweaked the end of the runway, ran it up to the maximum speed that the ministry would permit, which was 16,500, holding it on the brakes, let go of the brakes, and he was off in 600 yards, and just disappeared from sight in the clouds, and was flying for about 17 minutes, and then came in doing quite steep gliding turns, as though he'd been flying the airplane for weeks.
There were depressingly few to witness the event, and the only known record of that historic occasion is a still photograph and a fragment of 16mm film shot in defiance of the Official Secrets Act by an unknown amateur. What are Sir Frank's memories of that day?
Well, someone slapped me on the back and said, "Frank, it flies." And I suppose I was tense or something, and my comment was, well, that was what it was bloody well supposed to do, wasn't it?
The marked lack of official interest on the occasion of the first flight still rankles with Sir Frank 40 years on.
Only a group of, from Power Jets and a group from Gloucester's, and the group from Power Jets included the resident technical officer from the ministry. But there were no official representatives, and what I think was rather a scandal, there was no attempt to make any official films of the whole affair, and so no good film of those first flights exists.
By contrast, there exists excellent film of Germany's second jet, the twin-engined Heinkel 280. The construction and first flight of their original jet, the 178, had been so secret that not even the German Air Ministry had been aware of it. After the successful test flights became officially known, orders for 9 prototype 280s followed, with the promise that if satisfactory, substantial production orders could well follow. In a remarkably short time, von Ohain, backed by the full facilities of the Heinkel works, had designed and built a new turbojet, which gave 1,250 pounds of thrust on the bench to power the new aircraft, itself in many ways a most advanced concept which can claim a number of firsts. It was the first twin-engine jet, the first with a tricycle undercarriage, and the first to fit and later to use an ejector seat. The 280 was the second jet in the world to fly. The first prototype, this is actually the third, had flown from this runway at Marianne, the Heinkel Company factory airfield, on the 2nd of April 1941, 6 weeks before the British jet, the Gloucester Whittle, was to fly. It's instructive, therefore, to see the progress that could be achieved given adequate backing, and there is no doubt whatsoever that if Whittle's project had enjoyed the same facilities, the Meteor could also have flown by this time. Although the 280 achieved over 500 miles an hour and bettered an FW-190 in mock combat, no mean achievement, it did not, for political reasons, go into production. Neither did von Ohain's engines. The sole Allied jet in 1941, the E-2839, was, after its inaugural flight, extensively used to test fly a new Whittle engine, the W2B, installed in the Meteor. The E-2839 proved to be capable of 440 miles an hour, with an absolute ceiling of 56,000 feet, fully vindicating Frank Whittle's early claims for turbojets. However, the Whittle W2B was to prove a most difficult engine to develop.
I think many members of the team wished that we had gone ahead with the W1 air-cooled engine, W1A, rather than pushing ahead with the more advanced W2 series of engines, because the W1 engine had flown successfully, 10 hours flying with a brand new aircraft, brand new propulsion system, and never with the engine covers open once. And that, I think, must be an all-time record in aviation.
That success of the E-2839 led in some ways to an over-optimistic program for the Meteor. The ministry required 1,200 Whittle engines and 500 airframes. The question concerning Frank Whittle was who was to produce the engines. Relations with the Rover Company were then so bad that S.B. Wilkes, the managing director, went to Rolls-Royce to see his old friend Ernest Hives.
Hives sent for me one day and said, look, we're going up to Clitheroe tonight. We're going to have dinner with S.B. Wilkes. He didn't say why. So off we went, and we had dinner in the Swan and Royal in Clitheroe, old pub there. And after dinner, old Hives turned to Wilkes with his usual abruptness and twinkle in his eye, always did it humorously, really. He said, you know, you're making a hell of a mess of this jet job, aren't you? You don't get on with Whittle. And Wilkes said, yeah. He said, well, I don't know what you're doing with it. He said, you grub about on the ground, you know. It's an aircraft engine, it's our meat, not yours. I'll tell you what I'll do. I'll give you our tank engine factory at Nottingham. You give me this jet job. And Wilkes said I should be glad to get rid of it. And so we got all the Rover facilities at Clitheroe and Barnoldswick.
And that memorable dinner got Rolls-Royce into the jet aero engine business.
In the light of subsequent history, it was a remarkable dinner altogether. It was one of those 5 bob ones, you know, wartime 5 bob dinners. I can't remember whether Hives paid or Wilkes paid. I expect Wilkes did. Old Hives didn't would pull that one over, I expect. But it was a fantastic deal for Rolls-Royce as things turned out.
Next day, the two men went to the Rover jet production factory that Rolls-Royce had just acquired.
And Hives looked around and said, this will do as the experimental shop. Forget about production. We've got to get this engine right first, and then we'll produce it as easy.
The resources of what was, and arguably still is, the greatest producer of aero engines in the world was now at the disposal of Power Jets, with foundries able to cast intricate parts in steel or high-duty alloys, virtually unlimited stocks of high-grade steels and other metals, together with a large and highly skilled workforce able to utilize to the full the facilities available. A certain urgency was now attached to jet engine production. Mosquitoes of the RAF photographic reconnaissance units had been bringing back disquieting evidence, wispy outlines of unknown delta-winged aircraft and scorch marks on the grass airfields at Lechfeld, Peenemünde and Rechlin, the German equivalent of Boscombe Down, where this photograph was taken. These scorch marks were known to have been made by experimental jet aircraft. They could well have been made by the Messerschmitt 163, a lineal descendant of Opel's amusing rocket glider. The delta-winged 163 Comet, powered by a lightweight, liquid-fueled Walter rocket, had been designed as an interceptor fighter and possessed a truly amazing rate of climb. In October 1941, the prototype had broken the existing world speed record at over 623 miles an hour on the edge of the sound barrier. Rocket planes apart, a new jet was being tested in Germany by 1943. It was the Arado 234 Blitz bomber, the only jet bomber to see service in World War II, which it did during the Battle of the Bulge. But fortunately for the Allies, the 234 had suffered from a common weakness of German wartime research: too little and too late. Hitler had banked on a short war. By the time it was clear that this was not to be, there was insufficient time to develop the promising early prototypes, which in 1941, with victory scented, had been postponed. But there was another fundamental reason for delay. The Arado, for example, had been held up for 12 months, while the Junkers company under Dr. Franz were developing their jet engine, the Junkers Umo 004. It was certainly an advanced concept, an axial engine, that is, the simple, reliable Whittle-type compressor being replaced by these multiple blades, a difficult engine to get right even today, but it was theoretically more efficient, presenting a smaller cross-section, important in high-speed flight. Two were fitted in Germany's most successful jet fighter, the Me-262. The first flight was from the Messerschmitt factory airfield at Liebheim near Ulm. The date was July the 19th, 1942, and the pilot, Flugkapitän Fritz Wendel, who, in the absence of a propeller slipstream over the elevators, had to apply the brakes at 112 miles an hour as he passed a white line across the runway. He was later to report, "Immediately I touched the brakes, the tail lifted. The turbojets ran like clockwork, and indeed seldom have I been so enthusiastic during my first flight of a new aircraft." In fact, the 262 was tricky. The first two prototypes had flown with piston engines. This, the third prototype, was the first to fly on jet power alone. It had engines which required very careful handling. Too much throttle and the turbines burnt out, or the compressor stalled. Another unpleasant characteristic of those early axial engines was a pronounced lag in throttle response, which called for a very carefully judged landing approach. After the 17-minute first flight, test pilot Whittle slipped past the Gigant gliders that had been constructed in 1940 for the invasion of Britain, with just enough power on for a perfect approach and touchdown. But the moment he closed the throttles, no doubt in some relief, both jet engines immediately caught fire due to excess fuel igniting in the jet pipes. The fires were soon put out, but they were an omen of long delays caused by Luftwaffe indifference, and later Hitler demanding that the fighter be capable of carrying bombs. There were other problems with the engine, and 262s were not to see action until October 1944 to intercept the high-flying B-17s of the US Army Air Force. Out of 1,500 built, there were probably fewer than 100 262s operational and never more than 15 serviceable at any one time, all flying with engines that were so underdeveloped that more 262 pilots were lost in flying accidents than in action. Nevertheless, had they been available in sufficient numbers with an engine as well developed as Whittle's, they could have made even the losses to the US 8th Army Air Force unacceptable. As it was, they joined the Luftwaffe's piston engine fighters in the great air battles over Germany in 1944, and 262s accounted for at least 100 American bombers shot down.
I got those two at 2 o'clock. Watch them, Scotty.
At that time, the only operational Allied jets were 16 Meteor 1s powered by Rolls-Royce Welland engines developed from Whittle's design. The aircraft were hastily converted from a training to an operational role for 616 Squadron, the first in the RAF to fly jets, to intercept the very fast V-1 flying bombs. The first jet versus jet combats followed during the summer of 1944, though admittedly they were a little one-sided. The first American jet, the Bell P-59 Air Comet, was powered by two General Electric engines which were American copies of a Whittle W-1. The General Electric Company had built their version in just 4 months, but too late to see service. In September 1944, the Minister of Aircraft Production, Sir Stafford Cripps, visited Power Jets, and Whittle suggested the nationalization of the entire jet aero engine industry.
What I visualized was a single cohesive unit with Power Jets at the hub of it, you see. And I even thought it possible that I would be the chief engineer of the whole business, since we'd started it, and our engines were, in my opinion, still the best.
Sir Stafford came, saw, and confiscated. The only company to be nationalized was Power Jets itself, whose staff thus became civil servants. It was a blow to Frank Whittle, for with the end of the war within sight, the Miles Company had designed the M52, which was to have been Britain's first supersonic research aircraft, to be powered by a Whittle-designed engine, which would have been the first ducted fan. This and other projects were under intensive development. But the fate of the M52 project began a fashion to be followed by successive governments. In February 1946, when the design was 97% complete, it was cancelled, along with all the other advanced engine projects of Power Jets, which was to become simply a test facility for other companies' engines.
We were forbidden to design and make engines, and so that the people who'd started the whole business were robbed of the right to design and build engines.
Frank Whittle resigned from the board of Power Jets and retired from the Royal Air Force as Air Commodore. Most of his staff followed him and scattered throughout the industry at home and abroad. Thus, when the new shapes, some owing much to German high-speed research, were shown at the early post-war Farnborough shows, the major responsibility of British aero engine design and construction had passed to other hands. Frank Whittle's brilliant pioneering work was to give Britain its world lead in jet aero engine technology. It was, in the early post-war years, made freely available to all. Sir Stafford Cripps gave Rolls-Royce Neens to Russia to found their jet engine industry and to power their MiG-15s over Korea. Britain's second jet fighter, the de Havilland Vampire, was begun during the war, but too late to see service. At the 1949 Farnborough, the de Havilland Comet was shown to the public. It was the world's first civil jet airliner, and although tragically flawed, was the herald of the jet age in which, sadly, Sir Frank Whittle was to take no practical part. Although knighted and rewarded, he remains bitter to this day.
Oh yes, I am. But most bitter about firstly the fact that the policy mismanagement delayed the use of the engine in the war. It did go into operation, but in quite a limited way. Didn't have any material effect on the war. I was bitter about that, because it needn't have been so. And but even more bitter about the removal of my right to design and make engines. And one consequence of that was that the ducted fan, which is now practically universal, turbofan, was delayed for at least 6 to 10 years.